Section: Introduction. In this section, we introduce image generation as a key task in computer vision research, focusing on how it captures the data distribution of original image datasets to create high-quality synthetic images. Recently, diffusion models have emerged as effective solutions for learning these data distributions, surpassing traditional GAN and auto-regressive models. The diffusion process involves gradually adding Gaussian noise to clean data, and the denoising process estimates the score from this noise. Once we accurately learn the score function, we can generate data by solving the reverse process. We also discuss how diffusion transformers integrate transformer architecture into diffusion models, replacing the commonly used U-Net model. Evidence shows that, with enough training, these transformers can outperform traditional methods without needing long residual connections. However, their slow convergence remains a challenge due to high costs. Our goal in this paper is to address these significant drawbacks from a model design perspective. Classic computer vision algorithms typically use encoder-decoder architectures, favoring large encoders for feature extraction and lightweight decoders for efficient inference. In contrast, contemporary diffusion models mainly use decoder-only structures. We explore the potential of decoupled encoder-decoder designs in diffusion transformers, asking whether this approach can lead to faster convergence and improved image quality. Through our experiments, we find that the standard diffusion transformer struggles with balancing abstract structure extraction and detailed appearance recovery. Additionally, it faces limitations in extracting semantic representations due to reliance on raw pixel supervision. To tackle this, we propose a new architecture that separates low-frequency semantic encoding from high-frequency detailed decoding, which we call the Decoupled Diffusion Transformer, DDT. Our DDT model features a common encoder for extracting semantic features, which are then processed by a velocity decoder along with noise to estimate the velocity field. To ensure consistency in the features across adjacent steps, we apply both direct supervision for representation alignment and indirect supervision from the decoder's velocity regression loss. In our experiments with the ImageNet dataset at 256 by 256 resolution, our decoupled diffusion transformer, DDT-XL2, achieves a state-of-the-art performance of 1.31 FID with interval guidance in just 256 epochs, which is about 4 times faster than previous methods. For the ImageNet dataset at 512 by 512 resolution, our DDT-XL2 model reaches 1.28 FID within 500,000 fine-tuning steps, outperforming all prior methods significantly. We also enhance inference speed by sharing features between adjacent steps. We formulate the optimal sharing strategy as a minimal sum path problem to minimize performance loss. Our static dynamic programming approach identifies this optimal strategy with minimal additional time cost, resulting in a smaller FID drop compared to naive sharing methods. In summary, we present a new decoupled diffusion transformer model consisting of a common encoder and a velocity decoder. We introduce static dynamic programming to optimize self-sharing strategies, improving inference speed while minimizing performance degradation. Our DDT-XL2 model achieves state-of-the-art results in both ImageNet datasets, demonstrating significant advancements in the field. Section Summary. In this section, we introduce our decoupled diffusion transformer, DDT, model, which enhances image generation by separating low-frequency semantic encoding from high-frequency detailed decoding, leading to faster convergence and improved image quality. Our DDT model achieves state-of-the-art performance on ImageNet datasets while employing an optimal encoder sharing strategy to boost inference speed with minimal performance degradation. Section: Fast Diffusion Training. In this section, we discuss how to enhance the training efficiency of diffusion transformers through various optimizations. We focus on operator-centric methods that utilize efficient attention mechanisms. For instance, linear attention variants help reduce the complexity of training, while sparse attention architectures focus on relevant token interactions. We also explore reweighting techniques to stabilize training dynamics and representation learning enhancements that incorporate external biases. Techniques like REPA, RCG, and DoD integrate vision-specific knowledge into diffusion training, while masked modeling improves spatial reasoning by ensuring structured feature completion during denoising. Together, these strategies tackle issues related to computation, training stability, and representation. Next, we analyze linear-based matching, a specific type of diffusion model that we find particularly simple and efficient. For clarity, we sometimes use diffusion and matching interchangeably. In this framework, the initial time step corresponds to pure noise. As shown in our figures, diffusion models refine spectral components in an autoregressive manner. The diffusion transformer encodes noise to capture lower frequency semantics before decoding higher frequency details. However, this encoding process tends to weaken high frequency information, leading to an optimization challenge. This observation leads us to propose separating the traditional decode-only diffusion transformer into a clear encoder-decoder structure. We introduce a lemma regarding a linear matching noise scheduler at a given time step, where we define the maximum frequency of clean data. The maximum frequency retained in the noise latent is influenced by the time step. As time progresses, encoding semantics becomes easier, but decoding complexity increases due to growing residual frequencies. If we allocate more calculations to earlier time steps, we can improve performance, indicating that diffusion transformers struggle with encoding lower frequencies. Conversely, if we allocate more calculations to later time steps, it suggests that matching transformers have difficulty decoding higher frequencies. To identify the bottlenecks in current diffusion models, we conducted targeted experiments using a specific model and solver. Our findings show that focusing more computation on early time steps enhances final performance compared to uniform scheduling, revealing that diffusion models face challenges in later steps. This leads us to conclude that current diffusion transformers are limited by their ability to encode low-frequency semantics, motivating us to explore encoder-decoder architectures with strategic parameter allocation. Our proposed architecture consists of a condition encoder and a velocity decoder. The condition encoder extracts low-frequency components from noise input, class labels, and time steps to provide a self-condition for the velocity decoder, which then processes the noise latent to predict high-frequency details. We train our model within the established linear diffusion framework and refer to it as DDT, which stands for Decoupled Diffusion Transformer. The condition encoder is designed similarly to existing models but with improved features. It processes three inputs, the noise latent, the time step, and the class label, to extract a self-condition feature through stacked attention and feed-forward blocks. The noise latent is transformed into continuous tokens, and the time step and class label provide additional conditioning information. We use a technique to ensure consistency of the self-condition across adjacent time steps, which accelerates training convergence and enhances inference efficiency with minimal performance loss. Additionally, the encoder benefits from indirect supervision from the decoder, which we will explain further. Section Summary. In this section, we explore various optimizations for diffusion transformers to enhance training efficiency, including efficient attention mechanisms and representation learning enhancements. We propose a decoupled encoder-decoder architecture to address the challenges of low-frequency semantic encoding and high-frequency detail decoding, demonstrating that allocating computation strategically can improve model performance. Section: Velocity Decoder. In this section, we describe the velocity decoder, which shares the same architectural design as the convolutional encoder. It consists of multiple stacked interleaved attention and feed-forward network blocks, similar to DIT and SIT. The decoder takes the noisy latent representation, the current time step, and the self-conditioning feature as inputs to estimate the velocity. We assume that the class label information is already included in the self-conditioning feature, so we only use the time step and the self-conditioning feature as inputs for the decoder blocks. To enhance the consistency of the self-conditioning feature between adjacent steps, we use a method called ADA-LN0 to integrate this feature into the decoder. The decoder is trained using a matching loss that measures the difference between the data and the estimated velocity over a range of time steps. For sampling acceleration, we incorporate explicit representation alignment in the encoder and implicit self-conditioning in the decoder. This approach helps maintain local consistency of the self-conditioning feature across adjacent steps during training, allowing us to share this feature within a local range and reduce the computational load on the encoder. We define a set of time steps where the self-conditioning is recalculated, and if the current time step is not in this set, we reuse the previously computed feature. We also discuss a naive approach that recalculates the self-conditioning feature every few steps. Previous methods, like deep cache, have used this naive approach to speed up ImageNet models. However, ImageNet models trained only with a denoising loss show less consistency in deeper features compared to our DDT model. We propose a static dynamic programming algorithm to optimally construct the set of time steps. In our static dynamic programming, we create a similarity matrix for the self-conditioning features across different steps using cosine distance. The optimal set of time steps ensures that the total similarity cost is minimized, which is a classic minimal sum path problem solvable by dynamic programming. We define the cost and path tracking for this problem, and after calculating the cost matrix and tracked paths, we can find the optimal set of time steps through backtracking. For our experiments, we use the 256 by 256 ImageNet dataset with a total training batch size of 256. We follow methodologies from previous works like SIT and DIT, using the Atom optimizer with a constant learning rate of 0.0001 throughout training. To ensure a fair comparison, we avoid using gradient clipping and learning rate warm-up techniques. Our training setup includes multiple A100 GPUs, and we use the Euler solver with 250 steps as our default. We also utilize a pre-trained VAE with a downsample factor from Hugging Face and report various performance metrics. Section Summary. In this section, we describe the velocity decoder, which utilizes a similar architecture to the encoder, incorporating interleaved attention and FFN blocks to estimate velocity based on latent inputs and timestep information. We also introduce a static dynamic programming approach to optimize the sharing of self-conditioning features across inference steps, enhancing computational efficiency while maintaining consistency in the model's outputs. Section: Improved Baselines. In this section, we discuss our improved baseline models that incorporate recent architectural advancements like SWI-GLUE, ROPE, and RMS norm, which have been well validated in research. We also found that log-norm scaling significantly aids training convergence. By integrating these techniques, we created enhanced baseline models, as detailed in our results table. To ensure our implementation's reliability, we replicated the results for REPA B2, achieving metrics that surpass the original REPA findings, which boosts our confidence in our approach's robustness. Our improved baselines consistently outperform their predecessors without REPA. However, when we apply REPA, we notice that performance quickly reaches a saturation point, especially in the XL model size, where further improvements yield minimal gains. We present the performance of various model sizes at 400K training steps in our results table. Our Diffusion Encoder-Decoder Transformer, DDT, family shows consistent and significant enhancements across different sizes. For instance, our DDT-B2 model outperforms improved REPA B2 by 2.8 FID points, and our DDT-XL2 model exceeds REPA XL2 by 1.3 FID points. While decoder-only diffusion transformers hit performance saturation with REPA, our DDT models continue to achieve better results, although the incremental improvements are small, particularly in larger models. Regarding ImageNet, we report the final metrics for DDT-XL2 and DDT-L2 in our results table. Our DDT models are highly efficient, reaching convergence in about a quarter of the epochs compared to REPA and other diffusion transformer models. To align with REPA's methodology, we used classifier-free guidance with a value of 2.0 within the range of 0.3 to 1. Our models performed impressively, with DDT-L2 achieving 1.64 FID and DDT-XL2 reaching 1.52 FID in just 80 epochs. By extending training to 256 epochs, our DDT-XL2 set a new state-of-the-art benchmark of 1.31 FID on ImageNet 256 x 256, significantly outperforming previous methods. When we extended training to 400 epochs, DDT-XL2 achieved 1.26 FID, nearing the upper limit of another model with a 1.20 FID on ImageNet 256 x 256. We also provide final metrics for DDT-XL2 trained on ImageNet 512 x 512. We fine-tuned our DDT-XL2 model, initially trained on ImageNet 256 x 256 for 256 epochs, for an additional 100K steps. Using the same guidance interval, we achieved a remarkable state-of-the-art performance of 1.90 FID, surpassing REPA by 0.28 FID points. Some metrics in our results table show slight degradation, which we believe is due to insufficient fine-tuning. With more training iterations, DDT-XL2 reached 1.28 FID at 500K steps with CFG 3.0 in the same guidance interval. Lastly, we explored acceleration through encoder sharing. Our findings indicate strong local consistency in the self-similarity of our encoder. Even the initial state shows high similarity with the next state. This consistency allows us to speed up inference by sharing the encoder between adjacent steps. We implemented a uniform encoder sharing strategy, recalculating the self-similarity every K steps, and a novel static dynamic programming strategy. Our results show significant inference speedup with minimal visual quality loss when K is less than 6. The metrics loss remains small, while the inference speedup is substantial, with the static dynamic programming slightly outperforming the uniform strategy with less FID drop. Section Summary. In this section, we present our improved baseline models that incorporate recent architectural advancements, demonstrating consistent performance gains over previous models, particularly in our DDT family, which achieves state-of-the-art results on ImageNet with significantly reduced training epochs. We also introduce an encoder sharing strategy that accelerates inference with minimal impact on visual quality, further enhancing the efficiency of our approach. Section: Ablations. In this section, we conduct ablation studies on ImageNet with a resolution of 256 by 256 using DDTB2 and DDTL2. For our experiments, we choose the Euler solver with 250 steps as the default, without using classifier-free guidance. We train each model for 80 epochs, which amounts to 400,000 steps, with a batch size of 256. We systematically explore encoder-decoder ratios ranging from 2:1 to 5:1 across different model sizes. Our notation, DDT followed by the number of encoder layers and then the number of decoder layers, helps us represent these models. The experiments reveal important insights into optimizing the architecture. We find that a larger encoder improves performance as the model size increases. For the base model, the best configuration is 8 encoder layers and 4 decoder layers, which enhances both performance and convergence speed. Interestingly, the large model shows a preference for 20 encoder layers and 4 decoder layers, indicating a surprisingly aggressive encoder-decoder ratio. This finding encourages us to increase the layer ratio in DDT-XL2 to 22 encoder layers and 6 decoder layers to further investigate the performance limits of diffusion transformers. Additionally, we examine different types of decoder blocks and their effects on high-frequency decoding performance. We evaluate various architectural configurations, including simple 3x3 convolution blocks and basic MLP blocks. Our results show that the default setting, which combines attention with MLP, yields the best performance. Notably, due to the encoder-decoder design, even the basic convolution blocks achieve comparable results.